We can think of a battery kind of like a machine gun, because it's gonna have like sustain for a long time. You'll be able to keep shooting, and also a consistent stream, so consistent voltage, right? Consistent stream of voltage. But we can think of a capacitor more like a handgun or a pistol, like the Desert Eagle. And that's going to have like a small clip, but it's going to give you burst, all right? Burst of voltage. And so that's kind of the main difference between the battery and the capacitor. This thing might have like 5 bullets exactly, actually. If we really were to calculate it, it would have 5 bullets of time constants before it discharges itself completely. 5 bullets. Let's take a look at when something is in series. Remember that it's going to have the same current as it passes through all these 3 components. We can essentially say that I equals I, which equals I over here. That makes sense. And then, let's see. So we would have, all we're going to do is add up these voltages, kind of like the Kirchhoff loops we were doing. We would say that the sum of the voltages is going to be equal to, well, this one here would be epsilon. So we would just say epsilon over here. And then we would add, the next thing is going to be, if we come down here, we would be going towards this thing, so the resistor, VR, and so we would say IR over here. And then if we keep going down this direction, then we would come to the capacitor over here, VC, which we could actually represent with a Q over C. And so there we go. That's going to be for series. But remember, when something is in parallel, that current is going to be split into 3 different parts. So that's what we get over here. We're going to have the A current, here we would have the B current, and here we would have the C current. And we can see how it would basically start over here, and this would be the sum of all 3 of those. And then it would go over through here and split across into those things, and then come out over here as the sum of the 3 of those as well. A plus B plus C. So that's kind of cool. And that's kind of the rule that we would be writing over here, is that I is just going to be equal to I, depending on what those would be. But another interesting thing is that the voltages would be the same. So if we would have 3 identical 9-volt batteries, and these have to be identical components, but if we have identical components, meaning, so naturally everything has the same voltage, that's going to happen no matter what. But if they were actually exactly the same parts and stuff with the, other things equal, then these things would be A equals B equals C. And therefore the currents would actually be exactly the same as well. If the parts are the same, then the currents are the same, because the voltages are the same, because it's all going to be the same thing back and forth. Let's take a look at charging a capacitor, where the capacitor is going to absorb the battery's voltage over time. That's going to be epsilon. Well, first we can see that these 2 components are parallel to each other, because, yeah, and then also this is series like this. And now we're going to see if the time is equal to 0, and then all the way when the time is equal to infinity, and then what happens in between. Well, in between, you're going to have this time constant, which is equal to RC. And depending on what kind of loop that you're creating, what kind of circuit you're building, then different loops and different circuits would have different time constants. But that's just going to equal to whatever resistors in your loop and whatever capacitors in your loop. You just multiply those 2 things together. And you'll find that the time will increase if you have a greater resistor, then it's going to be basically the current's going to try to flow through these sections. And because the resistance is stronger, the current's not going to be able to go through there very easily. So it's going to make this whole thing last a lot longer, the charging process. And if you have a bigger capacitor, well, it makes sense. If you have a bigger capacitor, it's going to take longer to charge. So both of these 2 things are going to contribute to taking a longer time for this stuff to charge. Now let's examine just what the capacitor does by itself over time. We'll start over at t equals 0. We know that the capacitor by itself, with nothing, is going to have a capacitance of epsilon naught times the area, and then times the distance of separation. That would be this thing right over here. And then once we get towards the end over here, we can actually calculate the capacitance in a different way. We can actually say that C equals the charge that's on our capacitor, which would be Q, and then we'll divide that by epsilon. And that's going to be essentially the voltage of the battery over there. So we kind of have this Q over V situation, but that epsilon is pretty important, that it's literally just like the complete charge of the that battery over there, just so you kind of know, okay, yeah, you're going to put that epsilon into the capacitor at the end. And the charge is also going to be in there as well, so you can calculate the capacitance by dividing the charge divided by that. So that's kind of nice. Over here, we're going to have this other relationship. We could just say that Q divided by voltage on the capacitor, VC. So at any point in time, actually, and this would be sort of a function of time, so you're going to have like the Q of t or the V of t functions down over here. So at any point during the charging process, you can kind of also use the same relationship to calculate the capacitance in there as well. But at the beginning, there's no charge. You can't really calculate the capacitor with this, because it'd be like 0 divided by 0 or something. But you could just use that formula. So now let's analyze the charge on this capacitor, which is going to be this green stuff. Because, in the beginning, we have the Q equals 0. So that's just normal. But at the end, we're going to have Q equals CE, right? Because you can just rearrange that equation. But in the middle, when we talk about the Q of t equation as a function of time, then you'd have to go C epsilon minus C epsilon, and then there's this e to the negative t divided by RC. And you can kind of see that if time was equal to 0 over here, then this whole thing would be equal to 1. And well, this E constant, this would be equal to 1. And then you'd say CE minus CE would be equal to 0. So at time equals 0, you get Q equals 0. But at time is equal to infinity, then all of a sudden this thing essentially becomes a huge number. And then you're going to divide CE by a huge number, get rid of this whole thing. It just becomes 0, and then you get CE at the end. And so that's how you can figure out what the charge is on the capacitor. Well, let's do the same thing with voltage. We're going to start with V equals 0 at the very beginning. And then towards the end, V on the capacitor is going to be equal to epsilon. That's going to be this thing right here. So that's why we kind of interchange those. But during this whole process, the time function is going to be epsilon minus epsilon times e to the negative t over RC. So you can see if you plug in t equals 0, then this whole thing would equal 0. And then if you plug in t equals infinity, then this whole equation would equal epsilon. It's just like we did with the charge. Now let's discuss the current. So first, we got the IA, which is going to be coming through this section over here. And we know it's going to split off into IB and then IC right here. But we also know that now, because these things are in parallel, they're also going to have the same voltage. And this is going to get the full force of the voltage there, and this is going to get the full voltage there, those two resistors. But the capacitor is going to have 0 voltage, right? We've already determined that. So, zero voltage. If we wanted to calculate the current going through here, don't we know that IC is going to be the same for both of these? So we can actually use Ohm's law to calculate the current going through this resistor, which will give us the current going through that capacitor. So let's just say that if we want to find the current of the capacitor, we can use the epsilon, that's going to be the voltage going through that resistor, divide that by the R of that resistor, and you'll get the current going through the capacity at the beginning. Towards the end, we'll also find out that the current is equal to 0, because once this thing is done charging, no more current will go through it. It's done charging, so it doesn't need any more current. So that thing will just straight up go to 0, and then nothing will happen there, and then all the current's just going to go flow through here at that point. That's something to keep in mind. So yeah, and then let's go on to where the function of time would be. we'll use this thing, which is going to be epsilon divided by r, and then we're going to take the E, the negative t divided by RC. And so we're going to kind of use, again, the time constant and stuff to be able to calculate the current going through our capacitor. Now, if we were to increase the resistor here, increase the resistance, the current will decrease. And that's kind of important because sometimes you want to keep your capacitor like with a low current. You don't really want to kill your capacitor, so you might need a stronger resistor. Otherwise, you might just like destroy your capacitor. So let's plot out these things over time. We'll look at charge right here. Charge is going to start at 0, and it's going to reach a certain maximum Q at 5 time constants, 5 tau. It's going to be 5 of those, 5 bullets. And then at around 1 time constant right here, the charge is going to be at 63% charge. So it's going to need 4 more taus before it completely charges. Then we'll look at the voltage. Same thing. It's going to be kind of like a scaled version of that graph. So it's going to look exactly the same. And over here you'll have the max voltage. It's going to be VC. And that's going to be after 5 tau. And same thing where after 1 tau, you'll get 63% voltage. And then for the current, it's slightly different here. It's inverted. We're going to start with 0 current, and then, we're going to start with max current up here, where, epsilon over r. And then it's going to reach a 37% strength after 1 time constant. And then towards the end here, it's going to reach 0 after 5 tau. And awesome. This is going to be how the graphs look for charging a capacitor. Now let's try to discharge that capacitor that we just charged up. So it's going to be full of charge over here. And then we're going to take away this switch here. So that way this is going to be isolated current. And that for all the charge is going to come out of this thing and shoot through here. So it's going to be your the current. And it's just going to be 1 current. So all these things are in series. Okay. Now at time equals 0, we're going to have, we're going to see what happens there. And then at time equals infinity, we're going to see what happens there. And in between, we're going to have this tau equals RC again, same thing over there, where you kind of have to figure out what that time constant is. And depending on if you have a bigger resistance, then the current is going to struggle to flow, and so it's going to take longer for this thing to discharge. And if you have a bigger tank, then it's also going to take longer for this thing to discharge. That will give you a higher time constant. Now let's examine the capacitance, just like we did before. We'll start with the Q naught equals V naught, because if you just know the charge at the beginning and the voltage at the beginning, then you can figure out the capacitance from there. But we also have that relationship throughout the entire time here that says that Q as a function of t divided by V as a function of t could also give you the capacitance at any moment, because that relationship is always going to be constant. It's always the same, gives you that capacitance. And then over here we would have at the end where the capacitance, you don't have any charge or any voltage going through there, so you have to use the epsilon naught A over D equation again, back from the beginning. Now let's look at the charge. So we're going to go with Q equals Q naught at the beginning. Okay. And then towards the end, Q is going to equal 0. That makes sense. We're going to discharge the whole thing. But during this whole time, we can calculate Q as Q naught times E to the minus T over RC. And you'll be able to plug in T equals 0, and you would get that, you just get Q naught right here, or T being infinity, that would make this thing a really big division, and so you'd get 0 at the end. Next we would have the voltage. So we start with V equals V naught, And then at the end, V is going to be equal to 0. This is on the capacitor. And throughout this whole time, we can have V naught times e to the negative t over RC. We literally calculate it exactly the same way as we do the charge. Now let's try to figure out what the current is going through all this. In the beginning, it's going to be very strong because we have the entire charge, and then we have all these different resistors that we have, and then we have the C. Well, just keep in mind that if you have more resistors, you could actually lower that charge. But essentially, you're going to get the full charge of this thing discharging itself. And then towards the end, we would have the IC equals 0. At first, it was full, and so we get the full current, and at the end, it is empty. Now, during this entire time, we can calculate IC as a function of time using Q naught divided by the sum of the RCs times our little decaying thing, which we have here, negative T over RC times that E. And so that would just basically be very similar to these other equations over here. And so their graphs are going to actually look the same. Now let's look at those graphs of discharging the capacitor and compare them to charging the capacitor. So when we start over here, we're going to have a large amount of charge, which is going to discharge itself. And over here at the first time constant, we're going to get 37% of our charge remaining. So it's going to be kind of more like a little bit further down here. It's going to be almost discharged after one time constant. And then towards the end here, we're going to get 0 after 5 time constants. And that's going to be Q equals 0. Q equals 0 at 5 time constants. Over here, same thing with voltage. So we start up here with the max voltage, comes down here, at around here, going to be 37% after one time constant, and then voltage equals 0 after 5 tau. And for the current, well, it's going to be the same thing. So we start here at a max full current. It's going to come down here and reach I equals 0 at 5 tau. And over here, you're going to get around 37% remaining current after one time constant. So you can kind of see how the current is actually going to be the same chart for both charging and discharging, which is really important. Okay, so start at maximum and end at maximum at 0. Start at maximum and end at 0, both times. But these things are going to be different, you know, because it's charging or whether it's discharging. Now let's examine where we would use capacitors and resistors. In a power supply, we might want to have a lot of energy, so we would want to have a high capacitor. In a circuit board, though, we might actually have both parts, but we would want to have like high resistors and we would have low capacitors because we don't want too much energy and stuff and things blowing up. So we want to sort of keep the resistance up so the currents don't go too much, and we want to keep the capacitances low in the circuit board. But in a light bulb, you would want to have a low resistance so that way you get all the current flowing through there. You get a nice bright light bulb.